Hello everyone, I'm Dave Muller from Dave Muller Science, Art, Music. Today I'm going to take you on a musical journey through five-dimensional hyperspace. First I'm going to explain what five-dimensional space is. Then I'm going to put random five-dimensional notes into the five-dimensional space. Then I'm going to sort the notes using the traveling salesman problem. And finally, I'm going to play the notes so we can go on our journey through the five dimensions. So what is five-dimensional hyperspace? Well, let's start with one-dimensional hyperspace. And this is a one-dimensional cube. If you have a number between 0 and 1, you can plot that number somewhere on this line segment. To go to the next dimension, we copy what we have and connect the corners. Now I have a two-dimensional cube. I go from 0 to 1 in the y dimension and 0 to 1 in the x dimension. To go to the next dimension, I copy what we have and connect the corners. This is a three-dimensional cube. Now really it's a two-dimensional shadow of a three-dimensional cube, but on this drawing we can plot x, y, and z. So to go to the next dimension, we copy what we have Okay, we copied what we have, and now we connect the corners. And that is a four-dimensional hypercube, or a two-dimensional shadow of a four-dimensional hypercube. And so we have x, y, and z, but now we also have 0 to 1 for the next axis, the q-axis, for example. So how do we go to the next dimension? We copy what we have and connect the corners. And we connect the corners. Oops, I'm using the wrong color. And there is a five-dimensional hypercube. Here is a rotating five-dimensional hypercube I made on the computer. The lines are much straighter than the ones I drew. So what are we going to put into our five-dimensional hyperspace? Five-dimensional notes. And this is how I make five-dimensional notes. I have a computer program, and the first dimension is pitch, the second is duration, the third is loudness, the fourth is timbre, and the fifth is location. And all of these notes have a number between 0 and 1. And I have them all set to 0.5. So I can play a note, I can move the pitch up, or I can move the pitch down. And the same with the duration. I can have a medium length note, a short note, or a long note. I can have a loud note, a soft note. I can have a bright note or a dull note. I'm going to turn this up a little bit. And then I can move the note to the right speaker, or I can move it to the left speaker. Now I can also generate random notes. So this is what the score of random notes looks like. Each note has 5 values. They're just random numbers between 0 and 1. And if I play this score, not very interesting, just playing random notes. So now we're going to sort the notes to put them in order, using the traveling salesman problem. So what is the traveling salesman problem? Well, it's a classic problem in computer science. Given a set of cities to visit in a continuous route, what order of the cities is the total distance the smallest? So let's say we have a shoe company. And here's the United States. And say our shoe company is in Los Angeles. We'll call that city number 1. And then we open up a store in New York City, city number 2. And then our salesman just has to drive back and forth. Then we open up a store in Chicago, city number 3. It's still pretty simple. Our salesman just goes 1, 2, 3, 1, 2, 3. It doesn't matter which direction, it's the same distance in either direction. Then let's say we open a store in Miami, number 4. A store in Seattle, number 5. One in Houston, number 6. One in San Francisco, number 7. St. Louis, number 8. Denver, number 9. And I don't know, up here, 10. Number 10. Okay, what is the quickest order of the cities? Now the computer knows the distance between each of the cities, and I came up with this algorithm when I got in an argument with an electrical engineering professor, and he thought neural networks would be able to solve this problem faster than traditional means, and I thought he was wrong, so I had to come up with an algorithm real quick to show that mine was faster than his. Now the thing to remember is it is not possible to come up with the fastest algorithm. That's the trick. If you had 30 cities, it takes 30 factorial number of calculations to solve the problem, which is like 2.65 times 10 to the 32. So it takes all the computers in the world a really long time to solve that. But we don't need to come up with the best one, we just have to come up with a really good one. And so this is the algorithm I came up with. I take a deck of 10 cards, one for each city, and I take the first 3 cards off. a 5, 10, and an 8. So I go 5 to 10 to 8. Then the next card, a 9. So then I go, which one of these paths do I stick the 9 in to increase the distance the least amount? And it's obvious to the eye. A computer would try it in each path using the distance formula. The next card is an ace. The next card is a 7. Well, this one's easy. The next card is a 2. The next card is a 4. The next card is a 3. And this one's a little trickier. I bet it would be this one here. And the next card, of course, is the 6. Let's just say it's this one. Now we shuffle the deck. We measured the total amount, shuffle the deck, and try it again, and do it over and over and over until we get the shortest path. And this is the algorithm I came up with. Now, how do you find the shortest path in 5 dimensions? Here, we use the Pythagorean theorem to figure out the distance between each city. In 5 dimensions, we still use the Pythagorean theorem. So in 2 dimensions, the distance between 2 cities is the difference in their x locations squared plus the difference in their y locations squared. In 5 dimensions, we just use the difference in x, the difference in y, the difference in z, and if q and r are the 4th and 5th dimensions, the difference in q and r. So here is 500 points in 2 dimensions sorted in their shortest path. We will sort our 500 notes using the shortest path in 5 dimensions. And when we listen to the notes sorted in the shortest path, you will be able to tell where you are in the 5-dimensional space. The shortest path sequence provides a gentle, meandering, melodic journey through the hyperspace. At some point, the notes will be at the high-pitched, short, loud, bright left corner of the space. At another point, the notes will visit the opposite corner, which is the low-pitched, soft, dull right corner of the space. So as you listen to the notes in the sequence, imagine where you are in the 5-dimensional hyperspace. So that was all 500 notes played in order of the shortest path. So we heard the gentle meandering journey as short notes were close to other short notes and loud notes were close to other loud notes. What if we sorted the notes in the longest path? So how do you do that? I just put a minus sign in front of the distance formula. I call this the crazy salesman problem. Now here is 500 points in two-dimensional space sorted for the longest path. Compare that to the shortest path. Now if you look back and forth, you see the notes themselves are not changing. It's just the order that they are in the path. And in this case, it'll be a syncopated because we'll go from a short note to a long note and a loud note to a soft note. But you kind of hear a counterpoint because if I go from one note to the furthest away and then I go from the furthest away to this note, I wind up close to the first note. So it's almost as if we have a path of odd notes and a path of even number notes, but they're jumping across the five-dimensional space. So here is the 500 notes sorted in the direction of sorted in the order of the longest path. Thank you, everybody.